Okay, guys, now that we are getting into exponential functions, let's take a look at the basic equation of an exponential function. It is y equals a times b to the x. So notice our input variable x is the exponent. So that is why we call these exponential functions. So we have a times b to the x. So this is the first example of your handout. We are going to identify our a value and our b value. So in our first example, we have y equals 2 times 2 to the x. Our a value is 2 and our b value is 2. The b value is the base of our exponent, which is our variable x. So this value is very important in these functions. So before we decide if this is a growth or decay function, that means growth means it increases, decay means it decreases. So these are similar to linear functions. They will either increase or decrease. They are different than quadratics, where our parabola increases on one side of the AOS and decreases on the other. So let's find 5 points to graph to see what this function looks like. So we're going to plug in these x values into our function. So we're going to plug in -1 for x. 2 to the -1 is 1/2. Remember, whenever we have a negative exponent, it reciprocates the base. And 2 times 1/2 is 1. So we get an output of 1. So 1 point is -1, 1. So let's plot that point. Now we're going to plug in 0 for our exponent. So we're going to plug in 0 for x. So we have our a value 2 times 2 to the 0 is 1. Anything raised to the 0 power is 1. And 2 times 1 is 2. So we have 0, comma 2. So that's our y-intercept, 0, comma 2. Now let's plug in 1 for x. 2 to the first is 2. 2 times 2 is 4. So we get 1, comma 4. Now let's plug in 2 for our x. 2 times 2 to the second is 4. 2 times 4 is 8. So we have 2, comma 8. So 2, comma 8. And then our last ordered pair that we're going to graph is we're going to put in 3 for x. So input of 3. So 2 to the third is 8. And 2 times 8 is 16. So we get 3, comma 16. So 3, comma 16. So we have talked earlier this year about the asymptote of exponentials. So I'm going to pencil in our asymptote, which is our horizontal line that our graph, our function approaches, but it does not cross or intersect. So this is y equals 0. That's this x-axis. This is our asymptote. So I'm going to go ahead and put that here. Our asymptote is y equals 0. Now I'm going to create this graph. It increases. And then it gets closer and closer to this asymptote, but it never crosses. Because if we plugged in -2, we would get 1/2. And then if we plugged in -3, we would get 1/4. And we plug in -4, we would get 1/8, and then 1/16, and then 1/32. So it gets closer and closer and closer to 0, but it never touches or crosses. So this is what the graph of an exponential function looks like. So you can see that it curves up. You can also see our outputs. The pattern is going from 1 to 2, 2 to 4, 4 to 8, and 8 to 16. So our outputs are being multiplied by that base of 2. So it's doubling every time. We have a constant ratio In linear functions, we have a constant rate of change, but with exponentials, we have a constant ratio. So this 2, this b, being more than 1, tells us that we do have an exponential growth function. Our domain is from negative infinity to positive infinity, so we can use any x value to plug into our function, but our y values, the range, our graph, the lowest that it goes is up to the 0, that asymptote, but it does not ever hit 0, so we're not going to include 0, and then it goes up to positive infinity. Our y-intercept is 0, 2. That's an ordered pair. An interval of increase, our graph is increasing from negative infinity to positive. Just like a linear, an exponential is either increasing or decreasing. It does not do both. So we're going to use null for that. Our end behavior, as x approaches negative infinity, f of x, we're going to use our asymptote. So as our x values get smaller and smaller, our y values get closer and closer to that asymptote of 0. That is on the left side. And then on the right side, as x approaches positive infinity, as our x values increase, our y values also increase to positive infinity. Now, our average rate of change, we've not done that for a while, but all that is slope. So we need 2 points, and you'll always be given the x coordinates of the 2 points. So when x is 1, we can look at our chart here. When x is 1, y is 4, so that's 1 point. 1, 4, so that's right here. And then our next point is 3, 16. 3, 16. So 3, 16 is up here. So we are looking at the average rate of change of this secant line. So we're finding slope of rise over run. So we could count from 4 to 16 and then go over 1 or 2 units. I'm going to do it algebraically. So we're going to use slope formula. So y2 minus y1 over x2 minus x1. 16 minus 4 is 12. 3 minus 1 is 2. And our average rate of change over this interval is 6. So this is an exponential growth. Our graph is increasing. The b value tells us that we are increasing. We are doubling each time with our outputs. Another thing to note is your asymptote is going to be used for your range as well as part of your end behavior. So finish out the rest of these problems, then you can check the answer key in Canvas. I hope this helps.